Tartrazine, the first one.
Yeah, so click on that and OK.
Yeah.
In File, Open.
Right, date.
Yeah.
Saccharin.
Are they OK, those two?
Yeah, they're
So if
fine.
you click on Saccharin, then press Control-Shift,
Which one's
the arrow and the control
Okay.
at the same time. Click on Caffeine and OK. Right, okay, so now I'll label.
It's pretty similar.
Yeah, it was quite like this graph, didn't it?
Okay, and then we want 3 copies.
Yes, please.
So is this a perfect example of what we should have got?
Looks pretty close, yeah.
But no, this one here.
So
yeah.
it should look about. Yeah, this one looks pretty similar actually.
That's,
Oh, I've done alright actually.
It was done by me, so it won't be perfect. But it should be close to it, but not perfect.
yeah, that's good enough. Right, okay. So as you can see, that number's the wavelength of maximum absorption. 279 is a wavelength.
Okay.
And that's the absorbance at that wavelength.
Okay, so let me
Next
write
to
this
it.
down just to make sure I've got it right. Okay, so
What's the wavelength? The 279.
The big number, because obviously that corresponds with those, and
Yeah.
then that number, because that obviously corresponds with those.
so x equals the wavelength, and then y equals the absorbance.
Yeah. Right.
So the wavelength is the wavelength of maximum absorbance.
Yeah, so it's at the peak, yeah.
Okay, yeah.
So we're going to measure those individual ones at those wavelengths.
No, I shall explain that bit in a minute. Right, now, you've got to pick one wavelength and only one to program into the detector next week. For all 4 compounds.
Okay.
Because what happens is you'll make up mixtures, just quantitative standard mixtures that have all 4 compounds in the same volumetric flask.
So then you want to pick out by the
And
the
they
retention
get
times.
injected onto the column, and then so they all go onto the column together, but they travel through the column at different speeds, so they get separated.
Yeah.
And then go into the detector one at a time, and the detector is literally a miniature glass cuvette, just like the one you've been using there, with the wavelength that you've chosen constantly shining through it.
Okay.
So when just the solvent or the mobile phase goes through, it sets at 0 absorbance. Then when your packet of compound goes into that cell, the little cuvette, that wavelength gets absorbed and a peak is drawn.
Okay.
So
Right.
you need to pick a wavelength that
Yeah, so
corresponds to the
what criteria would you use? Would you think this would be a decent wavelength? No, absolutely not, because you'd get no signal for those, because those 3 compounds are not absorbing that wavelength.
So you want to be what, about here or something?
Yeah, good, but tell me why would there be a good place?
Because that's where your peaks are, more peaks.
Well, if you,
Oh, and you've got a peak for this one as well, which is there.
yeah, this is called an Abisca, so at the moment it's sat over 386 nanometers and showing the absorbance of that wavelength. What you can do, if you put the double-headed arrow, then hold the left button down on the mouse and drag, you can move it onto different wavelengths.
Okay.
So, obviously, would that be a good one to choose?
No, because
Yeah, because it's very sensitive. We call that sensitive when it's absorbing a lot of a given wavelength to vanillin, and virtually no
Nothing.
sensitivity to the other 3 compounds.
so we want one where they're all up quite high, don't we?
What you want is maximum sensitivity, but also the sensitivity to be similar for all 4 compounds.
We're going to want it to be around here, surely, because
Well,
these
if you want to move it around and look at those, what I suggest is you get those as close together as possible so the sensitivity is similar for all 4 compounds, but also as high enough level of sensitivity as you
Oh,
can
yeah,
get
yeah,
to.
look.
There's no 100% absolute right answer, it's just a sensible one.
look, these are all 0.6 something. Is it? I mean, how accurate are we wanting to go with this? Because we
That's
can,
good enough if you're happy with that. That's totally fine.
and that's at 258.71 nanometers.
Yeah, this doesn't get printed out, so write it down.
Okay.
You want the chosen wavelength, if you've chosen that
Okay.
one.
Chosen
and the,
wavelength.
And the absorbance of each of the compounds of that wavelength.
Okay, so the chosen wavelength
And how accurate can you go?
You can't. You've got. There's no 100%. You're actually asking a good question. If you realise there about precision, sometimes it's not. That's the best you can get with this. But what you would ideally want is a flat for all 4 compounds, but we haven't got that with these. In these synthetic analgesics or the opiate analgesics, we've got more of a flat,
So if we
rather than on a steep slope.
So then we want to put the absorbance for each of these in at that wavelength, yeah? So if the absorbance of the new is 0.603.
Yeah, whatever you do, don't forget to bring that wavelength with you next week, because we need that to program into the detector.
And how accurate will that go? 258?
Oh, okay. You mean in terms of it's you round up. There's no decimal
260.
places. That's an artifact of electronic interpretation. Wavelengths sort of generally aren't fractions of nanometers.
259 then.
Yeah, that's what we program in. Yeah.
Okay.
So hang on, what was that? 259. So then saccharin and then caffeine.
And you're doing yours at
What do
258?
we do next week? Then we make a solution of
Basically, you're going
and
to set a quantitative standards. You need to keep these you made next week for the qualitative side, because if you've got 4 compounds, each absorb that given wavelength, so you'll get 4 peaks. The thing is, you don't know which peak is what if you put them all in together, do you?
Yeah,
So you have to put the pure individual standards through one at a time to identify the peaks by what's called the retention time, and that's literally the time it's taken to go from the injector to the detector.
We've not got much left of our diluted. Look, we've got literally.
Oh, it's enough to inject.
Is that? Oh, you just need a.
Oh, you've been chucking it away,
don't-
have you?
Yeah, yeah, yeah.
Sorry,
It's just an injection, isn't it? So it should be
Yeah,
alright.
you only need to about 60 microlitres.
Oh, that should be alright then.
So there's your spectra.
Yeah.
Thanks.
So.
And then
Right on here.
next week you're going to create
There's a spare one.
quantitative standards
Yeah.
to create 4 calibration graphs,
Yeah.
which the calibration graphs you're going to use to work out how much of each of those food
Is in the
additives
product.
are in an unknown sample.
So hang on a second. So if we
That's
just
the
quickly-
crux of it, I see.
That's the bottom
So
line,
if we
yeah.
just quickly write on here, so 0.6, if I just, this is a spare one, so that there is the absorbance,
Yeah, there's no units for absorbance.
and this one here is the wavelength. Okay, and that's no units for the wavelength either, is it?
Yeah, the actual symbol for
Oh,
wavelength.
hang on, no, I've done it wrong. That's all right.
It's just this, isn't it?
Wavelength, is that
And
one?
then you put max when it's a peak next to it.
Okay, so this is here is lambda.
So that's the max. Max, yeah.
So you were saying earlier about the absorbance, the 1%.
The
what
Beer
was it?
Lambert law one, 1% volume.
So you have to work out the extinction coefficient.
The extinction coefficient.
That's in that Beer Lambert law
Yeah.
thing, and then that's that times the volume times the
Concentration times by the cell length path. So it's
The
1
suggested
centimetre.
wavelength is 258, 259.
yeah. And then we can't do the second part till next week when we've
Right.
tested them all at that wavelength. Is that right?
What's the second part?
Oh, hang on. I'm saying it wrong. This one here, the max absorbance. Is that just this?
Well, this one.
Yeah.
Oh no, you just do the same thing, but instead of using the absorbance, right? Well, just if you follow it literally, you're going to work out 1%. So work out your extinction coefficient again, instead
So
of using the absorbance.
So we
at
use
the
this-
chosen using the absorbance. Now, because it's a coefficient, it should come out the same number.
So when we've got these two, but you said to pick one peak to do this one, so we're better
Yeah.
off picking these peaks because they're like the ones that we're going to use.
It doesn't really matter, honestly, as long as you've got the corresponding absorbance to work out your extinction coefficient.
So we're going to use this one 257.82 for.
Yeah, and the absorbance is what
and
you
the
want.
absorbance
because the
is what they want.
formula is A equals ECL.
Okay.
E being the extinction coefficient.
Oh, so hang on. A equals E with that little thing next to it times C times L.
Yeah.
Right, cool. Thank you. I don't know what that sign is there, but I've noticed it was a little wiggly thing next to it.
Yeah, that's supposed to be, regardless of what your C, L and A are, that should stay the same.
For each different one? Or for
For a particular compound.
a particular compound?
Yeah.
Okay, cool.
So each type of compound, so tartrazine will have its own extinction coefficient value.
Okay. This is,
Vanillin will have
this
its
is
own
extinction
value, 'cause
coefficient.
Whenever it's called coefficient, it's generally, I'll say generally, regarded as a constant value,
Okay.
specific to your environment and chemical.
So this is the extinction coefficient, and this would stay the same for tartrazine, saccharin, vanillin.
Yeah, I shall give you a little hint about that. Convert your concentration into moles per centimetre cubed rather than micrograms.
Into moles, centimetre cubed. Okay, cool.
Alright.
Cool. Thank you very much
Brilliant.
for your help.
Thank you.